The opportunity to talk here. So I would like to say that like the kind of problem that we are trying to solve now, at least I do not have any particular idea like how to go about it and solve the problem. So it was quite frustrating. Here, like I had a lot of discussions with many postdoc students, and that I really enjoyed because I learned a lot, like a lot about new stuff, and that was really good for me. So that's it. And what I will talk about today is basically I will show you that in Mellin space some of the CFT calculations become really easy, and we can do some stuff there, and then I will again come back to this contact term issue that is there for Polyakov Mellin Bootstrap program. Although I do not have anything concrete to say about that, but I will make few comments on that, and then finally I will talk about AdS loops, like how can you fix some simple loops there which are not computed from the bulk side, so you can compute them using CFT data. So that is the plan of the talk. So we will consider 4-point function of scalar field and identical scalar, and as we know that we can write it in up to this scaling factor outside. We can write this in terms of z bar, and these are cross ratios, like the cross ratios u and v are defined in terms of z bar in the following way. Now so the constraint that we want to use is of course the crossing symmetry. So we can expand this in the S channel, and we can expand this also in the T channel, and block by block that equation doesn't satisfy, and therefore it gives us some constraint, and we can solve for the quantities that we are interested in that particular CFT. So this is the equation, and so what is the goal? So the goal is that we want to solve for this 3-point function, 3-point functions, and the dimensions and spin, right? So spin, for example, for this case, we know that only even spins can appear in the spectrum. So basically that leaves like what is the deltas and what are the C deltas. And that is the goal in mind, like, because if you can solve for them, then you can solve, like you know everything about the CFT that you are considering here. Now you know that you already have a formula for this. I mean, although the paper that I am talking about here is old, but now we have the inversion formula, right? So what inversion formula tells us is that we can write down this OPE data in terms of a inversion integral over z and z bar. Now there is a measure factor here. So you would say that, okay, then why should I go for, like, why should I use like another formalism or anything else? We can just use this formula, and that will give us all the data that we want to know. But as at a technical level, the challenge is finding this unusual block for a general dimension. In fact, finding the blocks for this 4-point function also is hard. But even leaving that aside, finding an expression for the unusual block is also hard, right? So you can calculate the data which is like in the light cone bootstrap limit, like z goes to 0 limit, the leading term that is universal, that you know. So for that term you can easily compute this. And we already have heard a talk few days back by Kollol, who showed like how to calculate the data for a leading double trace operator. Now the question is,
sorry, let me understand. The formula, that delta should be on the principal series?
This delta?
Yes.
In this formula, no. This so after while doing the Z integral, we will get the poles at a physical operator dimension.
So Z integral.
Yeah, the Z integral.
Wait, so the formula I'm familiar with is for the coefficients on the principal series, and then you've done some analytical
yes,
of that?
Yes.
And what is this? How is the Z integral related to that?
The J.
I didn't. Where is that analytic continuation in what you've done?
Yeah. Okay. So the question is, you start with that.
So physical dimensions will appear as poles of this C delta.
Yeah. I mean, to begin with, like we started with a formula where we have delta as a so here.
And Z and Z bar, what is I see.
No, do you want to see like how exactly the power comes? Like that's what you are interested in?
It's just a very stupid question. The question was that the paper I'm familiar with gives coefficients on the principal series, and I want to know how you went from there to the. You're working in physical dimensions, right?
Yeah. So basically, what I'm saying is, if you expand, like if you take the Z goes to 0 limit of this block and this block, like if you expand this also in the T-channel block, then you are going to get some powers, like you will get some powers which would be something like Z to the power delta minus let's say 2 delta phi minus 1. So when you compute the Z integral, you will get a pole in delta, and that's how.
When you compute the Z integral, you get a pole in delta, and then you
At
take the residue of that pole?
Yeah, you take the residue of that pole.
So that C delta there is some
yeah, this is
residue of a pole?
Yes.
So the right hand side, so that the right hand side has a pole?
The right hand side has a pole,
The
residue of that, yes.
Okay.
So you can just think of C delta L as a principal series, as you were saying, and that function is that.
No, sorry, what?
C delta L,
Huh.
it's just a function defined analytic function on the complex plane.
Yeah. I mean, when I said that it's not principal series, I mean that the deltas are not restricted to the imaginary line, but I can actually.
You have to go to you have to pick the residue.
Yes.
Fine. So the right hand side should have residue of pole?
Yes.
Okay. Residue of the function as a function of delta, right?
As a function of delta, yes. So okay. So as I was saying that we have already seen in the Kollol's talk that how to calculate gamma 0, L, which is the correction of a double field operator for n equal to 0. So this is the leading operator. But one would be interested to know what are other corrections to those double field operator with suppressed dimensions. So for that, there are two things. So one challenge is basically there will be contribution from the descendants of the lower n operators and also the operator that you are interested in. So there is both the combinations you have to take, and then you have to subtract the contribution of the descendants, and you will get the gamma NL you are interested in. So that is one thing. But there is another problem that if you really want to know the second term of the systematically the nth term of this block, then actually you have to solve a complicated recursion relation and get the coefficients. So these are hurdles. So right now, like if you see the recent developments, they have only, like using this formula, they have only calculated gamma 0, L. They
So you will expand this discontinuity G requiring T channel,
channel.
and then you will do this integration order by order.
Yes. Yeah.
In gamma 1L also you can compute, right, using this formula?
Using
Look at the next.
yeah, you can calculate. I'm just saying that you have to solve a extra recursion relation. So yeah, and there is no general pattern that you can guess there. So going to Mellin space, basically that doesn't get rid of the fact that you also have to take into account the contribution of the descendants, but this particular step you don't have to worry about.
Sorry, gamma 0, gamma A, this is like a double trace operator?
Double trace operator, sorry.
0 was what?
Sorry, so I'm considering some operator which is like
It's a number of
number of derivatives basically. So in the large spin limit, this would be some. Yeah.
Please do.
Yeah. So in the large spin limit, the number of derivatives is. So that is one thing, and then another thing is that this formula is not like it is only valid for spin greater than 1 because of this convergence issues, whether you can drop the arc term or not.
I'm sorry, so what you do is take operators like
Yeah. So
twist by twist or something like that?
yes.
Fine, okay. Identity gives you the leading contribution. Then. Okay.
Yeah.
Okay.
Yeah. So basically, I would show you like how we get gamma 0, L in our formalism, but then in that formalism you can calculate gamma NL like very straightforwardly. But it is true that you have to calculate all the lower orders gammas to evaluate gamma N, L. That is there. Okay, so and as I said that the formula that we will write down in the Mellin space that works.
I didn't understand the problem with computing gamma N, L here directly. Why can't you just take C at that value?
No, you can take. I mean, I'm saying that so what you have to do is you have to look for term up to z to the power n, like the n you are interested in.
Yeah.
So to get that subleading term, you have to and since the block is unusual. Yeah. So in the Mellin space, the blocks are defined for any general dimension in the following way.
And this formula will give me gamma delta gamma L for all L. Like
All L, yeah.
No, not for large.
The exact integration will give you for all L, yeah. Although I would show you, like I would go to large spin to show you some connection with this formula, but yeah, it works for any L.
Order by order calculation will give me answers which are valid for even small L's. As long as this formula is.
That is the claim, yes, that is the claim.
But if you take the contribution of only one operator or a few operators on the right hand side, that presumably is a reliable thing to do only at large scale, right?
This is the question I'm trying to asking you.
So that depends like whether you have a coupling or not. Like if you have a small coupling, then like say for example, if you have a CFT where you have in the leading order only terms like 2 delta phi plus 2n and so on, they appear in the leading order, and then you have only one singlet, say stress tensor, and its coefficient is suppressed in some coupling, say G, then in the leading order to correction of gamma 1 0, L, only this guy will contribute because double trace don't contribute. So.
But in more in general, there's a more general statement that large L is dominated by low twist operators.
Yes.
In any CFT.
Yes.
And finite L, you may be able to formally get the contribution of finite L from one operator that will not be particularly reliable.
Yeah, yeah, no.
Thank you.
Easy, because the estimated tools is not quite. Yes, sir.
Yeah. Question or anything? I should. Oh, I should pause. Yeah, sorry. So this is the definition of the Mellin block. Like I am defining the S-channel block. So that is defined in the following way. So it has these physical poles, and these are the shadow contributions. And imagine there is a factor like when so there is a factor which will give me 0 if I try to evaluate this at here. So they are really not there. Okay. So we are supposed to only pick up the physical contributions, and this is the Mach polynomial. And this factor is the crossing symmetric measure. So that is how my blocks are defined.
What is the interpretation of the denominator, gamma or delta phi minus S?
Oh, there should not be any unphysical poles at U, so they can in the S channel they get cancelled, but in the T channel, so this would become gamma minus T square, so that will cancel T square and so on. Yeah. So now we want to do the same exercise. Like we want to calculate. So we are thinking of a CFT where you have in the leading order like.
The left hand side is a block.
Left hand side is a block.
So you're giving the answer for the Mellin space representation of a block.
Yes. And this is for any general dimensions. So imagine a CFT where you have in the say in the leading order only like 2 delta phi plus 2n operators like these double twist operators. So it's like some MFT mean field theory like theory, and then you have a correction to this.
Sorry, why don't you write plus L?
Yeah. Sorry. And it has then order by order it has corrections and so on. And also you have OP coefficient. So these are the MFT OP coefficient and its corrections. Let's see how this formula works for here. So what we have to do, suppose we are interested in only in the n equal to 0, because if we are interested in other n's, we just have to keep all the powers, that's it. But suppose we are interested in n equal to 0, then we have to pick the contribution for s equal to delta minus L by 2. So that will give me power like u to the power delta minus L by 2, and then you plug in the information of this delta equal to 2 delta phi plus gamma, and then you expand that, because in the S channel there is no natural log u term. So the only way to get the log u term is to expand in anomalous dimension, and so this term will give you a factor like gamma 1 by 2 e to the power delta phi log u. Okay, so that is good. Now what happens to the rest of the factors? The rest of the factors, like the simplification that happens is for the Mach polynomial term. This particular polynomial for the choice of s equal to delta phi, like delta minus L by 2, this reduced to This reduced to a polynomial. So this is 3f2, but it's a polynomial because it has minus L, so it goes only up to certain order. And this polynomial satisfy orthogonality condition. Like this is an orthogonal polynomial in T. So
Sorry, what you plugged in your this is at G equals 0?
This is at G. What is G? Sorry, G equal to
Constant?
yes, yeah, G equal to 0. Because we are interested in the gamma 1, so already there is a G factor here because
That gamma 1 was on the left hand side?
no, we are just working with this. Don't worry about that.
So where did u to the power delta come? I don't understand.
There is u to the power s.
Which is integrated over, right?
Yes, so I'm picking out a pole s equal to delta minus L by 2,
I see.
and that's what it gives.
We cannot get a factor of coupling constant from polynomial.
You can get, but those will not lead, in the first order, they will not lead to the term u to the power delta phi log u. Because if you get G from there, then you can't expand this guy, and then there will be like power series. So they will contribute to the OP equation, OP coefficient equation, not the anomalous dimension.
So this form of the Mach polynomial that you wrote down was for specific choice of delta, right? Delta equals
G equals 0 basically.
Yeah, G equal to 0.
2 delta. Yeah, but what about delta phi? Delta phi is 1. Was a half or something like that?
No, delta phi is anything. I mean, here actually what I'm writing S is basically delta phi.
Oh.
Because S equal to is delta minus L by 2. Now delta equal to 2 delta phi plus L. So
That was P of delta minus H. What is H?
H is the D equal to H equal to D by 2. Sorry, the dimension by 2. Sorry. Yeah.
But if delta was anything, why is anything special? I mean, I didn't understand actually. If delta was free, couldn't I absorb G into a renormalization of delta phi?
If delta was free, like I can write down this expression also for like general delta.
Okay.
It need not to be that. But the point is that it has to be the leading power. So delta minus L by 2. So what happens is basically in this polynomial, there is a factor like delta minus L by 2 minus S m. So for S equal to delta minus L by 2, this only m equal to 0 contributes, and that term is this term.
leading twist.
It's
N equals 0, right?
n equal to 0, yeah.
That's what is going to happen. That's the input for this
Yeah.
simplification.
And I'm assuming that u goes to 0 so that I'm allowed to take only n equal to 0.
Yeah, I missed this. Could you say that again?
So T is a function of delta and L, or equivalently N and L, because delta, if you think of delta phi, plus 2N plus L.
Yes.
So T is a function of N and L. And for N equals 0, it's this.
No, I mean they are not, n need not to be 0. You just have to take the pole at S equal to delta minus L by 2. That's it. Delta could be anything, but only the leading, like S equal to delta minus L by 2, not plus 1 or anything.
Okay.
What will happen when you go to gamma 1 comma L, there will be a plus 1, and at that time that will not be a simple map.
I was thinking no n could be special because it could be absorbed into delta phi. You've not said anything about delta phi.
Yeah.
Yeah, I think S, probably S is special. Is that what's going on?
No, I'm
S equals.
so this guy has to vanish. That is what is happening. If this guy vanishes, then this becomes this. So okay. So just for clarification.
Particular delta, that's it.
Not delta, S, right? S.
I mean, delta minus n, particular delta minus n. That is S by the kinematics of this integral.
So this is the definition of the Mach polynomial. This is a 4f3, which you don't have to write. And then there is a sum where m plus n goes from 0 to L, and these are the Pochamars. Now, if S equal to delta minus L by 2 for anything, if S equal to delta minus L by 2 and this term becomes 0, then only m equal to 0 survive, and at that limit, this becomes a continuous Hahn polynomial. So, yeah.
So then it's not a function of S.
I'm already, which
It's already done the S integral.
I have already doing the S integral. That's why I'm plugging in S equal to delta minus L by 2, and then delta is this. So whatever S was there, those are actually delta
What
phi.
is that S comma S?
I'm so sorry. Sorry. So what I was trying to say is that once you get this polynomial, you can use the orthonormality of this guy, and you can invert the relation.
Polynomial is a polynomial in T.
Polynomial in T, yes.
Sorry, when you write S is equal to delta phi, you are assuming n is 0.
Yeah, yeah. I mean, because I'm doing the calculation for e to the power delta phi, but I'm saying that to be a continuous Hahn polynomial, the S need not to be anything special. It could be anything. The only condition is that it has to vanish. So
Oh, because you're picking up the pole contribution from S is equal to delta minus L by 2.
yes.
That's what's going on.
Yeah,
Because you're picking up that pole, that's why you're setting S equal to that
Yes.
value. And when you set that value, there's that simplification.
Yes.
So for that pole contribution, which gives you this.
Yeah, yeah. That's what I was saying. That
Okay, thank you.
coefficient of this. Yeah. So if we use the orthonormality of the 3f2 function that I wrote down before, then this is what we get. Okay, so I should also say that in the T channel, from going to S channel to T channel in the Mellin space, you have to do the following change of variable. That's basically exchanging U and P. And when you do that, as you can see that this measure would remain invariant, but only the appropriate S and T factors here, it will change. Now in the S channel you have a gamma delta phi minus S square, but this term would become minus T as you do that transformation, and therefore the measure factor which has this factor in the S channel it was cancelled, but in the T channel now this is not cancelled. So in the T channel you automatically get u to the power delta phi log u. It's a simple fact. You know this from.
You said this representation is valid in any dimension.
Yeah, yeah. I'm not assuming anything about the dimension.
For example, this quantity can be computed from Casimir equation in position space. So how this is?
Sorry,
how
again,
did you get
Casimir equation?
the block
Block, yeah.
in position space
Huh.
satisfies some differential equation.
Yeah,
And then you can solve this equation to get this solution for even dimensions, let's say.
yeah, yeah.
Now, here, this is more general than that. How did you get this expression in arbitrary dimensions? If the differential equation becomes simpler in this place,
It becomes a algebraic equation, and then you can solve the algebraic equation for any dimension.
okay.
Yeah.
So that's same differential.
It's the same differential equation, yes. Yeah, so the expression for gamma 1 0 comma L becomes so you in the T channel you pick just the pole at S equal to delta phi, and that will give you u to the power delta phi log u, and we want to compare u to the power delta phi log u of both sides. So I have already set in the T channel S equal to delta phi. So only T integral remains to be done, and I'm using the orthonormality of the 3f2 functions that I wrote here. So if I use that, then I will get an equation of this kind. So let me call this guy as BT, so it stands for T channel block. It's the same 3f2 that I wrote here. So now we have inversion like formula in this particular form. But notice this formula is not really same as the inversion formula, and the reason behind that is there is no suppression for double twist operator. So there is no double discontinuity or anything like that in this formula.
So there is a gamma of S plus T that's missing.
Delta phi plus T, S equal to delta phi.
Okay.
and gamma minus t square was cancelled by the lower factor. So
I didn't understand this.
which one?
Your right hand side had this log u and this f3 3f2,
3f2.
and then you are
Okay, let me write down that equation then. So basically what I am doing is the following. So I have in the left hand side the gamma 1 0 comma L up to some factor of delta phi, the 3f2 which is a function of t, right? And then in the
integration over t as well.
yeah, but we don't want to do that integral.
Okay.
Just leave it. Like see it as a polynomial in t. And in the t channel you just did the replacement, and because of the fact that this pole is not cancelled, so you get u to the power delta phi log u free. I mean you just get it, right? Okay.
It's a T channel I'm getting confused about.
Yes.
You're just taking that same block and interchanging U and V, is this right?
Yes. Interchanging u and v, and also like that factor, the
That
factor.
kind of
Yeah,
aspect.
yeah.
Okay, good. So here on the right hand side, you said that is just some replacement.
Replacement of this kind, S and T.
Okay, and now where you had u to the power delta minus L by 2, you should have got a v to the power delta minus L by 2.
Yes, yes, absolutely.
I don't understand. What are you trying to do with this?
So now I am saying that I want to equate my S channel u to the power delta phi log u term with the T channel u to the power delta phi log u term, right?
S channel u to the power.
Delta phi log u term with the T channel u to the power delta phi log u.
This is the part I'm sorry you're being so stupid, but I thought now the equation should be with the other channel v to the power whatever.
No. So what I'm doing is the following. In the position space language, I'm doing this. G u v equal to u to the power delta phi g v u. Now I'm comparing u to the power delta phi log u on both sides.
But that you can only do for the whole answer, right? Not for a block.
There should be some right? There should be some over delta.
There is a sum over L. I mean, no. Okay. So are you confused about the sum?
I'm saying why is it true that this is equal to? These two are equal. It's not true block by block, is it?
No, it's not true. Sorry. I gave something wrong then. Okay. Sorry, it's my mistake. So basically, I have in mind that I'm doing this, and yes. I'm solving a equation of this kind. Now I'm saying that I'm taking u goes to 0 limit, so my delta is only 2 delta phi plus L. So therefore there is no sum over delta, but there is a L sum still there. Okay, and now I have the same thing on the right hand side also, and then I'm comparing the powers u to the power delta phi log u, but there is this sum left.
On the right hand side, you have some more data also.
Yeah, delta and L. And in the left hand side only L sum is left, but 3f2 is orthogonal. I mean that will give you delta LL prime, so only one spin will left there. That's where the 3f2 is helping. Yeah, so okay,
You would get gamma as equal to inner product of the right hand side with one of your 3f2s.
yes. So basically in the right hand side I have u to the power delta phi log u, then T channel where there is a sum over delta L and everything, and I want to invert this using the orthonormality of 3f2, and that will give me an expression for
log u on the right hand side comes not because you're looking at some special value of
No, no. It comes.
every block has that.
Yes, yes.
This is done at every t. At arbitrary value of t, we equated both sides.
We equated both sides, yes. And then we use the orthonormality to get this relation.
And the problem is that if you have some polynomial in t, then that this integral kernel will say give a zero. That is the ambiguity in this language.
Sorry,
Suppose
again?
with this answer,
This answer?
yeah, the upper
This
line,
one?
how do you compare
Okay.
both of sides?
Uh-huh.
If I add the t to the power 2, let's say, plus t to the 2,
Here you add a t to the power 2.
outside, which is the answer? Some polynomial in t.
Okay.
But if log u takes t to the power 2
I mean,
or not?
yeah. I mean that will be there.
Log u.
Yeah.
I just want to say that this integral, because we are just picking poles, I know there are some ambiguity. I'm trying to understand, is it this kind of ambiguity that if you add something which is purely a power law in t and cancel the extra gamma factor suitably, so that does not have any pole, then this integration does not give, this integration is sort of divergent. So
Yeah.
this is the sort of the beginning of the ambiguity in this
No,
language.
but I mean what I'm doing throughout, I mean it's just the usual block. They are not Witten block. So to begin with, there is no ambiguity. But the ambiguity we are talking about is, I think, this, that if you don't have a pole piece and if you add some additional regular term, then if you integrate it, you will get the same answer. So those sort of ambiguities.
Yes, because you are supposed to equate them after you have done the t integration, but you are comparing at the level of integrand. This is true if the integrand kernel has no zero modes. Right? If you are comparing the integrands directly,
No, he's doing the t.
Yeah. At the end, I will do the integral.
3f2 is a polynomial in t,
Yes.
and there was an integration over dt on this side.
Yeah. So basically, the point is you can do in principle the integral, but then you will not gain anything.
This is
So-
what I am saying. You are comparing at the level of integrands.
Yes. Let's say yes.
I am just trying to understand.
No.
Comparing at the level of integrands. Now, you can do that if
No, actually, what he was saying, I mean, I'm pretty sure that will also give you 0, because at the end I will use the orthonormality of that, and then you have to complete the integral. You see?
say that kind of thing addition will give
Yeah, because so there is no pole in the right hand side. If you so if you add a plus t square here, then if you can close the contour on right, then this will vanish, right? Because there are no pole.
It would have to be a total derivative at every value of v, right? Because this right hand side is a function of v. That would be tough, right?
yes.
Yeah. It's like a Fourier transform. It's basically unique.
The Mellin space is nice because it immediately allows you to pick this u to the delta phi log u term.
Yes.
Even in the t channel. Otherwise,
Yeah.
in the t channel, I would have a hard time, right?
No, but in the t channel, log u is obvious, right? Because if you look for the limit u goes to 0, you get log u on its own. So you get log v in S and log u in the t, just term by term.
You can add a term that depends on v and t. That's probably not. Is that allowed in your?
The main point is that for Fourier transformation, you have no function which sort of integrates to the Fourier transform to 0 other than 0.
Right.
But here, if you have some, because the contour integration, if you have something which is purely a polynomial, forget let's erase all the measures. If you have something which is purely a polynomial, first of all, this integral transformation is not well defined because it is divergent integral. But if the regularization is such that they pick the poles, then that goes to 0.
Right. So the kind of thing we would want is a polynomial divided by v to the power t.
Yeah. So only a polynomial, everything gets cancelled.
Yeah. And is that allowed? Is that the kind of thing you're allowed to do? You're allowed to put v dependencies? I thought the only v dependence was here, but those were supposed to be functions only of s and t.
Yeah, I don't know. If that is the truth, then you cannot.
Yeah, I think that's how it is for Fourier transforms, right? Your function of x is a function of x. You're not allowed to put k in. Then you do a Fourier transform. You have e to the pi kx to a function of x. Even there, if you were allowed to make that thing a function of k, you could do funny things. I think.
So if I keep v to the s and u to the s and v to the v.
And nothing else in the whole thing should depend on u and v.
Yes. Now if I have something like a squared, all
A squared, sorry. S squared.
A squared. Then if I do S integration, suppose the final quantity does not have anything other than 1 S squared.
1 S squared, good.
A squared.
But you have a u to the power s.
Yes. And now.
Now you got, that won't integrate to 0, right? Because u to the power s itself has a cut. And if you've got an s squared, that will contribute to the cut.
You got rotating. I mean, depends on how this is. You are saying that S to V to the S will have a branch cut,
Yes.
and
You'll pick up a, at least it's not obvious that you can, maybe there's something, but it's not clear.
Sorry, what is the question? Is the question about how well defined the Mellin cut?
Indranil is asking, can you add some function of S and T here that will integrate to 0 for every u and v? That's basically his question.
Yes, so if you have S square, then this integration is divergent, even if you take from the class. So either you give me a regularization prescription, in which this will go away, or it will give a finite answer.
But it might be u and v dependent finite answer. Sorry, you guys know more about it.
No, what is the cut?
You suppose,
I'm saying ds, b to the s, S square.
oh, okay, you're right, not a cut. S to the power u. U to the power s is just something that goes, but it's not a, it's a function that blows up, right? A function that blows up something. So you won't be able to give you a 0.
Small u.
You need to
Right.
give a regularization.
I need to give you regular, it's just not clear that there's anything that integrates to 0.
Sorry, I
Small
don't-
u is
Yeah.
okay, right?
Small u?
Sorry, I.
No, but there's always some, there's always some part of the S plane where it blows up. Oh, you're saying mod u is small.
Mod probably you are using mod less than 1 or something.
Yeah.
But then what about S near 0? Somewhere in the S
Well,
plane.
the contour of S is
Yeah.
This
There's a theorem, right, that there's no analytic function that has no singularities.
Yeah. So this integral transformation
No,
will
but
have
the contour
problems
is
for
like
those
this.
functions.
Oh, there's a particular quantity, yeah.
Everything can happen on the left.
Okay. Okay. Maybe he can say, the question is, given u to the power s, v to the power t, is there a function of S and T or the class of functions of S and T such that that is identically 0?
At least not well defined probably, not 0 because
Well,
divergence.
if it's well defined, not well defined, you define
So-
it however he's defining
so-
it, and then is it 0? That's your question, right? That's ambiguous.
So
One
this,
regularization given is it 0?
Yeah. Is there some function which?
I don't know.
this is the question.
This is the question. Are there functions for which, however you define that integral, that for those functions it will be 0?
For example, f of st is a square, just a square. How do you define the integral?
No, I mean,
This has to be a solution.
but that's not a 0, right? So if it's just a s square, then
I don't know what is the answer. How do you do the integral depending on that?
so
What is
basically,
the
That's
yeah, the contour is the like any vertical coordinate like in the S plane, like some minus I infinity to plus I infinity with some shifted according to you. Now on this contour, like usually I would like to think if there is a pole kind of thing, I would deform the contour and see whether I can drop the arc. Then that's how I will do it. But if this is some polynomial kind of thing, then the integrated over on this line is not 0, right? I mean,
I'm not saying it's 0. I'm saying how do you do the, is it convergent or something like that?
is it convergent? I mean, I don't think it's convergent, right? Because it's just growing. So if you go to I infinity,
What is the prescription for doing the integral? You need to give a regularization. I don't know. I'm asking, how do you do this integral if it's a square?
no, if the integral is not well defined, how do you do the integral?
For those functions, this transformation is not well defined.
Yeah, I mean, that's, yeah, I mean, how can you integrate putting any function?
Forget that.
Yeah, same here.
General, I mean, just generally speaking,
It's a question about Mellin transfer.
it is a question about uniqueness of the Mellin transfer.
I mean, somehow I have this, I'll say why I'm bugging this. I know I'm bugging you.
No, no,
I'm trying
it's-
to understand, is this the genesis of the big problems that
No,
are
no.
at the
No,
ends?
no.
That's a different.
I mean, if you are thinking of the contact term in the Mellin basis, I mean, Polyakov Mellin bootstrap, then that is not related to this. That much is for sure.
That is totally.
Yeah, that's. Yeah, but like I can't give you an example of any function
I mean,
which will.
Fourier transforms are defined for a class of functions.
Yeah.
In strict sense. Okay.
But how do contact diagrams look like in the Mellin space?
They are up to this measures. They are some polynomials in SMT.
Alright, so there is this measure.
There is this measure, yes. Otherwise, you don't pick up the pole like double poles. Yeah. So you get an integral of this kind where you are integrating over this 3f2. So you use the orthonormality, and now there is no L sum on the left hand side. It's just single object gamma 1. But on the T channel you have all the operators present. So depending on like twist or anything, like you need to justify what are the operators that will contribute, etc. So now let's look at the large L behavior of this 3f2 functions. Okay, because this only here there is a L, this same L appears. Otherwise, it's the exchange operators in the T channels. So there are like ways to do it in different ways. One of the way that that is the fact that this 3f2 comes from a Wilson polynomial, which is a 4f2.
Ways to do what?
Huh?
Ways to do what? Now, what are you trying to do?
I'm trying to compute the large L expansion of this 3f2.
Of that three.
Yes. And now I'm saying that this 3f2 can.
You have to some well-defined function, and you're trying to.
Yes. Yeah.
Okay.
Yeah. So the large L expansion of this 3f2 that we are interested in, and now there are I'm saying that there are two ways to do it. One way is that this function comes from a well-defined 4f3, which is Wilson polynomial, and Wilson has already worked out the asymptotic series for that 4f3. So you can use that asymptotic series and take the limit so that you come from 4f3 to this 3f2. So that is one way. Another like easier way to do this is to define. To define the Mellin-Burns representation of this 3f2, and then what will happen is you will see that you will get two kinds of pole, and one kind of so let me write the thing.
So this 3f2 was a function of what? Wasn't it a function of
T.
T?
Huh.
Yeah.
Oh, are you confused about S?
Yes.
S or delta phi?
Yes.
Sorry. So if you define the Mellin transform of this in the following way, that let's say d zeta, z to the power minus zeta, and some function zeta. Okay, this z at the end of the calculation you set it to 1 because this is 1. So this is for any z, but
Z is T.
no, I'm sorry. At the end I want to set z equal to 1 after doing.
I don't understand. Is that function of T or not? Left hand side.
Oh, yeah. That's this t is there. Z is the argument.
I'm really sorry, but on the left hand side, where you had it, I thought you just got some function of T.
Function of t, and then z is set to 1. But I want to
What was Z? Where you were 1.
Yeah, 1.
So you're promoting it to a larger function.
Yeah, I mean because I want to define this
Okay.
particular thing.
Okay, fine.
And after coming back to this space, I mean, I will set
So
Z
you're
to 1.
Mellin transform in Z rather than in T.
Yeah.
Okay, fine.
To get the last one. So what I'm saying is, if you do this, this is nothing but just the Mellin bunch representation for a 3f2 functions. So these are bunch of gamma functions, and then these gamma.
Yeah, I just want to tell you that I have no idea what a 3f2 function is. So if that's
Yeah, I mean.
but okay, it's something. It's something that has a Mellin bunch representation, which is a bunch of gamma functions.
Yeah, it's so for this purpose, I think it's okay to know that you can write down a Mellin-like transform for this 3f2, which has argument z.
Okay.
Now, what I'm trying to say is the following: that this f xi, this Mellin amplitude or whatever you call it, this function will be bunch of gamma functions, and then those gamma functions will have two sets of poles, and one sets of poles if you pick up. So this summation is over that poles. So if you pick up those poles, you will get a series like this, and you will and another set if you pick up, you will get a series, and then the point is those series will have term if you take the large n limit like this, L to the power minus L, which are exponentially suppressed. But we are interested in like large spin limit, which are like power law like series. Because we have in mind this calculations done by ALDE and all, like how to reproduce those results and generalize those calculations. So we just pick the one set of poles, and that particular term has this form.
So you just want to pick the pole which gives you the 3f that you want.
Yeah, so there are two sets of poles. That's what I'm
Which
saying.
gives you same 3f.
Yes. This 3f2 will be done by having two sets of poles.
Sum over.
Yeah, sum over. Yes.
And one of them is important at large L, and one of them is less important.
Yes.
Fine.
And then at this point, actually, now things are interesting in the sense that if you look at this factor, then this is the double zeros at integer t's. So this is nothing but if you use the reflection identity, this is nothing but giving you a factor like sine square pi t. And if you calculate the double discontinuity of a t channel, that is actually sine square pi t v to the power t, right? So by going to the asymptotic limit, you actually generate the double discontinuity. So in that sense, the large spin and the inversion formula are actually sort of same thing.
Sorry, but the inversion formula double discontinuity appears in general, not just at large.
Oh, then so that is what the claim is, that if you do this summation, then that should go down up to j, like large spin perturbation theory and inversion formula are.
Oh, because the other one is L to the minus L.
Yes, yes. So that is the question that I was asking in Kollov's
Oh, I
talk.
see.
Yeah.
So you are saying the exact L expression,
Yeah,
in addition to having 1 over L corrections, also has exponential corrections.
that's
coming
what we
from
get.
this weird term.
Yes.
Oh.
So why they don't show up, I don't know. I mean, that is what I was asking them.
So the explicit answer that Kallol showed,
Huh.
that just has 1 over L corrections.
One over corrections, yes.
The inversion formula doesn't capture these terms?
Um,
L to the minus L terms?
I don't know, but his claim is that both are same, right? So they should not.
What was his claim?
That large spin, whatever you get from this resummation of large spin series and from inversion formula, they agree.
Right. But that means this is not captured.
Yeah, this is not captured. At least in our formalism, we get terms which has this behavior. So I don't know.
So can
Yeah.
I just ask, like, so you started out with the f of xi, right? You wrote the Mellin bunch representation
Huh.
at f of xi.
Huh.
You had like you did something to that, and you had like two sets. There were two sets of poles
Yes.
for that object.
Yes.
That's in the set of gamma functions.
Huh.
You look at larger, there are two sets of poles.
Yeah, so if in one set of pole, if I do a large L expansion, I would see that the power goes as L to the power minus L. In other set, this is the thing, and here the power doesn't go as L to the power minus L. You get some L to the power minus some
But
series.
both of them give you the 3f2.
These both terms should, yeah, that will give you the exact 3f2, yes.
But I thought it was like one of them was dominant, one of them was subdominant, something like that.
No, that is in the large spin limit I'm saying.
But
Like
for this is for general.
for general, yeah, I mean, I don't see any reason why it should
So
not be.
then my question is that, like, you have, so 3f2 is some hypergeometric function.
Huh,
So it will solve a differential equation of some kind.
huh,
Right.
huh.
So I was wondering if you can look at the limit of large L for this differential equation, and then its asymptotic. I mean, when you try to analytically continue in L,
Okay.
And if you can move from like one branch of solution to the other, because this L to the minus L kind of this thing is sounds a bit like some kind of, no, it's not actually. I was thinking of maybe non-perturbative ambiguities in.
I was thinking exactly the same thing. Sometimes you sum perturbation theory
Right.
and get a non-perturbative answer. If that perturbation theory has a...
But this is not like that, right?
I mean, it would have been more like e to the power.
Yeah.
But maybe it's something non-standard. I don't know. Is the large L expansion, is it convergent?
This one or this one?
Whatever you do,
Yeah, I'm doing for this. This is convergent, yes.
it's convergent.
Yes.
Then it doesn't sound like...
Because at large L it goes as 1 over L to the power fixed.
Yeah,
Fine.
yes. In fact, there is a better parameter. I mean, that's what I was saying, that these functions are, if you see, there is a pattern like L plus delta phi plus alpha, that is some independent term, and then L plus delta phi minus alpha, and then L plus delta phi plus beta, L plus delta phi minus beta. Now, if you have a gamma function of this kind, ratios of gamma functions, the better parameter to expand in L goes to infinity is not actually L, rather it's this parameter which is more suitable to do an expansion of this. So basically you can write down that any such ratios of gamma function has an expansion is j to the power 2k and some coefficient. These coefficients are exactly known, like in closed form. These are some generalized Bernoulli polynomial, but they are just known functions. So you get a series expansion. So two things happen. One is that you see that there is a term like sin square pi t, which is like a double discontinuity, and you have the same conclusion as the inversion formula, in the sense that which operator should contribute at this order and etc. And here the terms, they actually themselves organize in terms of j, and this was actually an input in usual bootstrap contribution, and like you just assume that gamma takes this form, but in this formalism, like you see that it has this form, it comes out of the calculation. So these are called conformal spin. So yeah, that's so.
More generally, are you saying that the inversion formula misses non-perturbative corrections in L?
But is this non-perturbative?
No, this one is not, but there is no, yeah.
That's not non-perturbative. Well,
No, that is
about
not
minus L
non-perturbative, right?
Some other non-standard.
But we see that there is this term. I mean, I don't know. So that, I mean, that is the reason I had that question, why it doesn't capture that.
The 3f2 asymptotic series for large parameters in those combinations.
In those combinations, 3f2 has?
As in, like if you have an L,
Huh.
you take L to infinity in that.
Huh.
Is there an asymptotic series that captures the behavior of 3f2 on that limit?
Yes, there is asymptotic series also, and they match, like this term.
Right, so you said that those series were convergent.
No, this series is convergent. The large L limit, this series is convergent.
Just because this is conversion doesn't mean that there is no
Yeah.
non-perturbative corrections.
But
They are not
this
required
particular
to-
series is convergent.
Yeah. Oh, okay. This is like one branch or something.
Yeah.
But typically, singularities of this form set the radius of convergence of the, what is it called? Of the, what's that thing? Borel transform. The Borel transform. So typically, you have such singularities which give you the radius of convergence of the Borel transform. Now, if the Borel transform has a radius of convergence, the original function is divergent. I mean, that's usually how it goes.
Yeah. So so what I was trying to say is, so at the end, since you have now gamma 0L and you have the expansion of this 3f2 in terms of j to the power 2k, so in conformal spin, you know now every term in closed form. So that was the thing I was trying to say. Yeah, in the last spin limit, like for any dimensions, now systematically you know all the terms in a closed form. And then the calculation for n equal to 1 and 2 is just the repetition of the same with taking the descendants. So yeah, so that is what I was trying to say here. Now one can do, instead of comparing the powers of the e to the power delta phi log u, if you compare the powers of e to the power delta phi, you get the corrections for OP coefficients, and they have the same arguments and they arrange themselves also in the powers of j. So that is that. And now, if you compare these two approaches, like so now I want to talk a little bit about the Mellin Polyakov Bootstrap. So the idea is that in Mellin Polyakov Bootstrap, instead of having these blocks, you are using
How does one go to G square order? Are we going to talk about that?
just yeah, that's the last part. So I just want to make few comments. That's it. So Polyakov Mellin Bootstrap tells you that you sum over the three Witten blocks, like 3 channels STU, so that the crossing symmetry is manifest. Then up to a contact addition of contact terms, this you can also expand, instead of those usual conformal blocks, your 4-point function in this particular decomposition, where the crossing symmetry is manifest, but you have the extra poles at s equal to delta phi plus n. So those cancellations of those poles will give you the consistency equation in this language. Now what we were trying to see is the following, that the equations we get from this and the equations that we get from the usual bootstrap that I solved before, like whether they agree, like so that the answers actually are the same. So what we saw is the following, that if your T channel has a singlet contribution and like there is no contribution from double field operators, rather, like those with 2 phis, then this approach and the other approach, they agree exactly. And if the T channel has contributions from double field operators, then these two don't agree. So there are some contact term business going on for that case. So that is what. And just to see that really that is the case.
Last time, which side were you expanding in the single trace and which side were you expanding in the double trace?
No, I'm saying that I have an equation of this kind, and I have also a bootstrap equation that we get from, like what I did there. So let me write it like this. Now writing down this equation in the Mellin space, I am comparing the equation, the powers of e to the power delta phi log u from here and here. Now if my T channels of this term and the T channel that is there, if there is a only a singlet exchange, then at order gamma 1, these equations and these equations are exactly similar.
Only singlet exchange meaning what, sorry?
So there are no contribution from, let's say, operator which is like double field operators.
Meaning it's just by phi itself.
The only phi can appear, then it's fine. But if this kind of operator appears where you have 2 fields, then it won't.
Sorry, but all these things are in the S channel. You take them into the S channel, right?
No, suppose if they contribute, like it depends, like for example, if you consider a theory like Polchinski did in his paper of this holographic CFT kind of thing.
Okay.
then you have a contribution in the T channel, right? The way.
Which is the T channel, please? At last time, what you were doing, on one side only a few operators were contributing.
Yes.
The other side, lots of operators. Which of them was S and which
So
was T?
if those lots of operators are just
If lots of operators, was that T channel?
yes,
Okay, fine. Please go on.
and then I'm saying that
I thought all of them were like the double trace kind.
no. When I'm comparing these things, I'm assuming that there are some minimal twist kind of a thing, so that only some finite number of single trace operators are contributing.
That is the T channel side or the S channel side?
That is the T channel side.
T channel is finite number of operators. S channel, lots of operators.
No, sorry. So what I'm trying to say, in the S channel, there is only one operator, that is n equal to 0, like in the calculation I showed.
Okay.
In the T channel, the operators are actually a sum over delta comma L, but you have generated a term like sine square pi t. Now what does that do? When you will take a contribution of a physical operator, that is t equal to delta minus L by 2, so that you have a sine square pi delta minus L by 2. Now if deltas are like 2 delta phi plus 2n plus L kind of term, then this is 0, right? So only the singlet will contribute. Then I'm saying that whatever singlets is there, and at that level these equations and these equations are same.
So you're saying if you that factor or kills the contribution of like double trace kind of things, and then the two things agree.
Yes.
And this is in this happens in like lowest order G or something like that.
Yes.
So you're saying the two things agree at lowest order G.
Yes.
Okay.
In the next order, we went in the next order and we saw that there is
They
a
don't
disagree.
agree. Okay, so the perturbation theory in G, there's a problem at some order.
Yes.
Okay, fine.
But how do you do perturbation? How do you go to the next order?
We just expand up to G square, assuming a operator
No,
spectrum.
but in the T channel, so in the beginning, at the leading order, you just took some singlet operator, as you say, in the T channel.
No, T channel I have written down as a sum over delta L. Now whatever is there, it will contribute. There is no assumption going up.
Okay,
Going
fine.
on.
So there's a bunch of single traces.
Yeah, bunch of single traces.
Which would give you some Ramos dimensions for the double trace tower,
Yes.
the 2n and L tower, and N tower,
Yeah.
right? And
Yeah.
now, what is the prescription to go to next order?
And just one question, so I understand this. In the context of Wilson-Fisher theory, if you had U1 symmetry, then there's no single trace operator. They're all 5 bar.
Yes.
Yeah, this is more like holographic.
This is more like the holographic.
Yeah.
And then how do you go to the next order? I'm asking.
In the to go to the next order, you have to expand the block up to gamma square, right?
No, but on the T channel, what do you do?
Yeah, on the T channel also you have to expand up to. So
No,
basically
operators.
what I'm trying to say is there are also double trace operator that will appear,
I
right?
think you're asking about where the triple trace operators will come.
No, I'm asking. So first of all, this is sorry. I mean, the way one does this, even if you want to go to the next order in G squared, you don't want to include the NL tower on the T channel, right? That's like double counting. I mean, why would you include?
No.
you want to
In the
see-
in the T channel for the next order. So let's say if I call the next order correction gamma 2, then in this gamma.
that were there already.
No. In the gamma 2.
Like T squared, but why phi squared? So let's call your phi as a probe field of delta phi dimension. So you have phi NL operators in the S channel,
Huh.
and in the T channel you have, let's say, T operator.
Yeah.
Okay.
You have what? T operator, huh?
Okay. Just one operator.
Okay.
And now you computed whatever
Yes.
you call this.
Yes.
Right.
Yes.
The attraction that it causes.
Yes.
Right. And now to go to next order in G, in the T channel I wouldn't put in the anomalous dimension that I got, right? For phi NL operators.
No. You
I
would.
just put T operator or T
No.
square.
No. If you just put, I mean that is not the right thing, right? You have to like. So assume that gamma 2 is the second order correction of those delta NL operators.
Yeah.
Okay. So this gamma 2 will get a correction which is proportional to gamma 1 square. So gamma 1 square is the leading corrections. And that's precisely because of this fact that now they contribute. They are suppressed by gammas. So you will do a sum where you are doing the sum over n.
First, actually, I'm getting totally confused with the context. Are we like in Wilson-Fisher theory, or holography, or something else?
No, the only assumption is that there are some double twist, double field operators like 2 delta phi plus 2n, and
Okay.
also one singlet, say.
Okay, so this would be a good assumption in the context of something like holography,
Okay.
where the operators were something like the stress tensor. You can exchange the stress tensor, you can also exchange multi.
Yes.
So on which side are you exchanging single trace?
In the leading order, only in the T channel.
Okay.
No, but the subleading order, if you want to satisfy this equation,
Hmm.
you don't want to include those double trace operators
No,
also
but
on
they-
the T channel side, right?
No, T channels, but they will appear. I mean, that's the whole thing. I mean,
Once you equate a bunch of T channel.
okay, let me tell you like how do I
then the sum would always be crossing symmetric, right? This is how you would think of crossing symmetric. Why? I mean,
Okay, let me say ki how do I calculate gamma 2 like this guy, gamma
Okay.
2. So then maybe, yeah. So,
I'm sorry to interrupt, but one side is primarily single graviton exchange, second side is primarily double graviton exchange, right? If we think from the point of view of bulk, which is S and which is E?
so the S channel, so the T channel is where primarily the graviton is exchanged.
The T channel is the single graviton exchange.
Yes.
And the S channel is primarily two
Double.
gravitons.
Not two gravitons. Oh, your probe particles
Particle
are.
scale, stress tensor.
No, let's take the.
Okay, two scalars, fine. Two particles.
Yeah, two particles.
So S channel is the double trace and the T channel is the single trace. Thank you.
Yeah.
Okay, thank you.
I think, yeah. And then now I'm asking the next order.
Yes.
The way I would frame this question is have two gravitons exchanged in the T channel, right? I wouldn't exchange two particles in the T channel. I would exchange two gravitons and look at their effect on the two particles in the S channel. In the same set of states. Phi square. And then
Yes, I see.
otherwise why would I, and then the sum would be crossing symmetric. Sorry, yeah, maybe you can tell me.
yeah. Okay, so what I was trying to say is like in the next order, I will get a term like this, right? Yeah, so in the next order expansion, if you do the block expansion, you get a term like this. Now you ask your question, like what
Yes.
What
now,
is the confusion?
Now
I want to
compute all
solve
these
for
things.
gamma 2 n comma L.
Yeah. So you would equate this to the T channel.
I would equate this to the T channel, yes.
Yeah. What is the T channel?
The T channel,
The T channel would still have your singlet operator, right? Not any of these operators, because this is already put in here.
okay, so if you, so this I wrote for the usual bootstrap case. So in the usual bootstrap case, the way you solve it is, so basically here this term is log square u, right? So this term will get mapped to log square v in the T channel. Now log square, now if you look at the individual blocks, then this has a behavior like log v. So, so you have to reproduce a log square v. So you have to do a re-summation kind of thing. So you take the gamma 2 and also if you have, so if your gamma 1 n comma L has infinite support in L, meaning non-zero for, then you have to sum over this and this to reproduce a term which is proportional to log square V and this guy. And if it doesn't have, if it has finite support, then only this term you have to resum to reproduce a term which is like log square V in the cross channel. And in the bootstrap language, like at least for a holographic theory, like when I say holographic theory, I mean that you have only operator of the kind like 2 delta phi plus 2n, 4 delta phi plus 2n and so on. There is no singularity yet, okay, up to the order I am talking about. So in those theories, you can calculate like, so in one side, so basically what will happen, this gamma 1 n comma L, depending on what interaction in the AdS bulk you are considering, this L would be non-zero up to that spin, right, depending on what kind of interaction you are taking. So it has a, it is non-zero only up to finite, say L naught.
Sorry, just a second. So you're saying, okay, so here you already fixed the problem, you solved the problem, right? Gamma 1 and C1 is known. So to some extent you solved it. The only new piece of information is
Gamma
C2
two.
and gamma 2.
Gamma 2.
Right, and how would you get that?
Yeah, I mean that's what I'm. So,
Okay.
so in this kind of theories, or so in this kind of theories, like I would take the bootstrap equation, like say in the Mellin space. Okay, so in the S channel, the operator that will contribute is gamma 2, 0 comma L. So, and if L is not equal to L naught, then from S channel there would be no other contributions. Okay, because up to L naught there is a gamma 1 term, so you would also get proportional to gamma 1 term. But if L equal to not equal to L naught, then only the gamma 2 appears at this order, right? And in the T channel, you would get a term which is proportional to gamma 1 square. So all the spin which are not, finite up to certain spin, those will contribute in the T channel to reproduce the gamma 2 0 comma L for all the higher, like L greater than L naught. But if you take L less than L naught, then on top of this there would be some term which are proportional to gamma 1 and C1 for L less than L naught. Is that
Somewhat clear, but I didn't quite understand it. I mean, if it is not what the main point that you want to discuss, we can talk about it later.
okay? But it's important that you calculate gamma 2 0 comma L, because that will help you to fix the AdS loops.
Yeah, that's
But only those gamma 2 0 comma L which has no finite piece contribution, meaning the gamma 1 term is 0. Only those L would help to fix the AdS loops.
But from conform field theory, how do I know that at the second order is the two graviton exchange that I have to look at? How do
No,
I know that
you
I'm producing naturally the loops in the AdS?
No, you are asking about loops in AdS now, or what?
Yeah, in the next order,
Huh.
this gamma square order,
Huh.
how do I know the operatorial content?
Oh no, you don't know about the operator. That is an assumption of the theory. You are assuming something that only up to double trace operators appear or something, and then you do the exercise. I don't think there is a rigid, solid understanding like what operator you should consider. That's an assumption. But of course, I mean, I think there is one reasoning, like if you have a loop, then you can at most cut like 2 particle kind of a state. So only up to double trace it can appear. And then if you go to 2 loops, then up to like I think 3 multi-trace, like 3 trace or something, that kind of operator can appear.
Right, but if I
So
don't know about AdS, if I just know this bootstrap equations,
Huh.
how do I recover all these things?
You were interested to know like how do I know like what operator will appear at what orders,
Yes,
right?
what new operators start appearing?
Yes, I mean at least in this calculation you don't see it.
So
you have to
if
assume.
If I insist that only one single trace operator appears even at the next order, is there some issue in solving this equation?
In the usual bootstrap equation?
Yeah.
No, I don't see at least any equation. And you can calculate it. And you will calculate precisely this way that.
But that's totally inconsistent from the bulk side, right? What kind of bulk is it telling me about?
No, if there is a singlet in the spectrum, you're saying that is,
No, I mean, at the next order also, I assume that there is only a singlet in the spectrum.
huh?
Maybe this log has to exponentiate. Maybe that will give you your multiple.
Yeah. So in other words, there should be some issue with solving this log square, getting this log square.
Getting a log square. Yeah, I think so. It's the kind of thing that normally happens.
Like, but at least in this order, you can solve for this term, like in the usual bootstrap. I don't know about ADS story, but you can solve for it.
So Abhijit has understood what's going on, but I'm still lost on it.
Yeah, yeah, sure.
What I'm putting it in a context, like n equals 4 what I'm understanding is that if I take some simple low dimension single trace operators on one side, which I think we're calling the T channel, that is reproduced largely by exchanging double trace operators on the other side. Okay? And now you're doing some perturbation theory in something. Is that 1 over n firstly?
It could be 1 over n also.
Okay, good. So then you're doing perturbation theory in 1 over n. And now the T channel side was exchange of some single trace operators. And if I just had those single trace operators, where is my perturbation theory? What am I correcting? How am I correcting that side of the vector? I think that, yeah.
T channel am I correcting?
I mean, suppose I'm thinking in terms of the inversion formula. So suppose I know I just have single trace exchange, then I can take that and re-expand that in terms of other blocks using inversion formula. And that's once and for all, it's done. Where is the perturbation?
Well, because you are getting
So,
not
see,
a solution to crossing because the derivative is a block here. You have to exponentiate the most dimension.
you're asking like what would be the correction of the due to the exchange of single trace operator, like in the next order?
Yeah, I'm saying there are two sides to your problem. One where you're exchanging small single trace operators.
Yes.
The other way you're primarily at least exchanging double trace.
But that is the story only in the leading order.
Okay, good. So how is it corrected? Firstly, the side where you're primarily exchanging single trace operators, how is that corrected?
In the next order.
Yes.
In the next order.
I think you're calling that the T channel. So
Yeah,
how's the T
T
channel
channel.
corrected in the next order?
So, like I would think that there should be, I don't know about this n equal to 4 SYM because that example I didn't do, but if there is a single trace operator, I mean, so if it should also have some corrections to the dimensions and the OP coefficients of it, and that will enter into the next order. If you don't know that and say ki no, there is no other corrections, then it will not contribute.
So it will be just, for instance, if the operators were the stress tensor between gravity, then we know the 3-point functions of stress tensors are not corrected. Or maybe they are. Maybe you get some. Maybe you get other structures. Is that the point?
If they don't contribute, if they don't get corrected, then I don't see anything that will.
Oh, maybe they do get corrected. Maybe. Okay. What about a theory like Polchinski's, in which there's no single trace operator other than identity?
Yes.
That doesn't get corrected at all then?
So there is no single trace, right?
It's all identity.
Yeah, I mean, so to gamma 2, you get only contribution from gamma 1 square kind of a term.
I'm not following your details. On T channel side, you're getting contributions only from exchange of identity.
So I think with the Polchinski solutions, you just think of that solution as gauge freedom. Any solution you have, you add a Polchinski solution to it, it's a good solution. The only thing that constrains the gauge freedom is the regime bound.
Okay.
That's how I understand Polchinski solutions.
Okay.
Always a solution.
Okay.
Perturbation theory.
Okay. Yeah, but just at technical level, I'm not understanding.
Yeah,
You've got
yeah.
a right hand side, which I'm calling T channel, and a left, primarily single trace exchange. Left hand side, S channel.
So-
I want to understand what is your, what is the correction order by order on the right hand side? The T channel, the single trace part. If
So,
it's just
so
single trace exchange, what it is.
can I answer this question using Polyakov Mellin language?
Okay, sure. Sure.
So in that language, what will happen is you have to, like, if you are looking for, let's say, 5-4 theory, then I take that contact diagram.
Yeah, what is the analog of the single trace exchange?
In this theory, there is no single trace, that is first. I mean, I'm considering a theory in the bulk, which is,
This is Polchinski's theory.
yeah, this is Polchinski theory.
Okay, good.
So suppose there is a term which is only this contact term is there. So I know this contact term. So by hand, so in my basis, WS, WT, WU, I'm also adding this contact term. Okay. Now this T and U channel, this channels starts contributing at order gamma square. So if my perturbation theory is in, say, I have a correction like 1 by n plus 1 by n square. So these channels, T and U channels, they starts at gamma square. Okay. And the S channel, where there is a double trace exchange, these with the contact term you can fix. And that will be non-zero only up to finite spin. Like that is the feature of the holographic theory, right? And in the usual bootstrap language, you solve it in the following way, that you have, so basically you have to compare powers of log u and log phi. Log u and log phi, that you have to compute in the first order. Or in this language, if you see, then you have to reproduce a log square v term in the right hand side. So sum over gamma 2 0 comma L has to be equal to exactly this term, but on the right hand side with the replacement u and v. So to answer, like, what I understand is in the T channel there are double trace exchanges. That's what is correcting.
That's what's going on.
Yeah.
But if you were doing this large L expansion, the double traces that exchange in the T channel are at small L. Is this right? At small dimension.
At small dimension. What is dimension? Sorry. 1 by L to the power tau, you are saying that?
The dimensions of the operators.
So this large spin stuff will not work in the leading order if you have only 2 delta phi plus 2n kind of corrections, because those are finite piece corrections and they are not captured by this, say, either inversion formula or whatever. Like the leading solutions like gamma 1 n comma L, for example, you can't reproduce this Polchinski like theories solutions using the inversion formula. You can't do that. You can only do that at next order, because these contact terms are not captured, right? The double disk would be 0. So that's why.
I'm sorry, I'm just going to try again. Give me one context, one concrete context, in which I can understand what is the right hand side and what is the left hand side. Any concrete context.
Okay.
If Wilson-Fisher theory is good, that's good. If holographic theory is good, that's good. But I'd like one context in which I can understand what you're doing. It's too abstract for me.
Okay.
But one very concrete thing.
Okay. So for example, in a
and can you reword your results in that concrete context in 2 minutes?
Yeah, sure.
I know what you're doing applies more generally, but just one context where I can understand.
Yeah, okay. But you want it in the usual bootstrap languages?
I don't care what language, just what is your final answer? And what is the left hand side, what is the right hand side? What are the operators contributing?
Yes, okay, fine. So I'll just use what I understand. Okay, this is the equation.
Which is the theory?
I will tell you now. So consider a theory which is Polchinski-like.
Okay.
So therefore, I on top of all this, there is one contact term. Fine.
Polchinski-like, which means that
I'm taking like the theory corresponds to this like
particular
543
contact term in the bulk.
particular contact
Okay.
term. So I have added that term.
Yes.
And now I would solve for
Sorry, your basis has only S channel written block.
there is S and also T and U, but like T and U in the after writing it in the, they are the same. They contribute same. Let's say 2 times this guy. So it means consider like only S and T. That's fine.
Your 4-point function is written in terms of only S7 blocks or S and T both?
No, it was written like S plus T plus U. I have just written the consistency condition which are set to 0 in this form. So that like in his language I can say what is on this side and what is in this side. So I'm interested in calculating the corrections of this kind.
Lovely.
And then in the S channel
And you're interested in doing this at all L or at large L?
at all.
Okay.
In this channel,
So largely what you did previously was large L calculation.
large L calculation, but I'm saying that you can also extend them to
Okay.
finite span.
Fine.
This will this particular term proportional to gamma 1 will appear in the S channel. If I also plug this expression in this T channel,
Yes.
then this would become gamma 1 square. So gamma 1 square meaning n square, 1 by n square. So to leading order, this channel can't contribute. So then what will contribute? This channel contributes, the contact term. So I get a solution gamma 1 0 comma L only for L equal to 0 equal to whatever contribution I get from the contact term. And rest of the L's don't get corrected at this order. Now I go to the next order, that is gamma 2 0 comma L, which appears here. And for L equal to 0, there would be 2 terms and all. But in the T channel, like it's systematically whatever appears in the double twist operator. But here now all the double twist operator that has gamma 1 square non-zero, they will appear here. So here the contribution would be, but since gamma 1 is only non-zero for L equal to 0, so all this kind of operator 2 delta phi plus 2n 0 comma 0, these operators appear in the T channel to give you the gamma 2 0 comma L at next order.
So the first statement that this was 0 was basically the statement that this contact term exchanges only spin 0 classically, right?
Yes, yes.
And now the second statement that you get more is somehow some loop statement or not?
The next order statement is about loops, yes.
Okay, fine.
Yeah.
So can I make a comment about this answers that you wrote down for the second order corrections for these operators?
Sorry,
So one
this
can understand, yeah, that one. So one can understand this gamma 1 squared term and gamma 1 C1 term as coming from the exchange of phi NL operators in the T channel, right? Because the gamma square would come from the double discontinuity. One gamma would come from the double discontinuity, and the other gamma would come from either gamma or C would come from.
so it depends because
Reynolds dimension or
so it
something,
depends
you know.
because if you are looking at the T channel, then if the operators are only double traced, like then double field operators gamma like only proportional to gamma term, the double disk would be 0. So the only term that will have a non-zero double discontinuity is gamma 1 square. So that will be in the T channel.
No, I'm saying in the T channel, if you insert phi NL operators, then they have already generated some Reynolds dimension, right, at leading order.
Huh.
So that gamma 1 would contribute to this.
No. In the leading order, phi NL can't generate any gamma 1, right? Are you saying that
Wait,
they will contribute to gamma 2? The phi NL operators will contribute to gamma 2 n comma L, but not gamma 1 n comma L. Because that is what we showed, right? That sine square pi t factor tells you that gamma 1 n comma L can't get corrected because of double twist, double trace operator exchange. in the T channel. So just for last time, can you repeat again? Like what is your confusion?
I'm interested in getting all these numbers.
Yes.
It's a C2, gamma 2.
Yes.
See, gamma 1, C1 I already obtained
Huh.
by exchanging some T in the T channel,
Huh.
looking at what they do for 2 pi and N.
Huh.
Right. And now, in order to get, so the new information is in C2 and gamma 2.
Yes.
And there is a second order correction coming from, first order corrections also, the square of first order corrections, gamma 1 squared and gamma 1 C1. So those I would think would come from the exchange of phi and L in the T channel.
Oh, acha. 5, 5.
Because there you would get a contribution,
Yeah,
which
yeah.
is double discontinuity. The double discontinuity contributes gamma and L,
Yes.
right?
Yes. Oh,
and,
you are just
and
looking.
then there is a correction coming from the B coefficients
Yes.
and also the anomalous dimension.
Yes.
So those would explain this last two, the 2 lines, the bottom 2 lines.
Yes.
That one and the other one.
Yeah.
But the first line would come from genuinely new contributions.
Yes. So that will be proportional to like these terms. So this is log square u. So the log square v that gets mapped.
No, forget the last 2 lines. I'm just talking about the first line now. Yeah. So how would that come? Right. That's the new contribution.
Yeah. So that's what I'm saying. So gamma 2 n comma l. So the way I will calculate is basically I will just plug in here and solve for S and T channel, and that will be proportional to gamma 1 square. Like right now, whatever I explained.
So you are saying that gamma 2 is proportional to gamma 1 square?
Yes. Yeah.
Gamma 1 square is just there, the third line.
Yeah. But the term has to be log square v. So gamma, it's proportional to gamma 1 square, but not necessarily this term. So that is the statement that is telling you that loops gets fixed by tree level data. So it is just that statement.
Now, what stops you from completing this to all orders? You could complete it to all orders.
Yeah. So what we are trying right now is basically this particular thing has a problem that new operators can appear, right? And without that, the CFT is not complete.
How do you know?
Because if you do the large spin analysis, then the conclusion is that if you take phi, then to reproduce the correct powers, you have to have 2 delta phi plus 2n kind of operators. Now, if you take the same, those 2 delta phi plus 2n kind of operators correlator, then you need 4 delta phi plus 2n operators. So this way you can say ki you need something like 2m delta phi plus 2n kind of operators. Like CFT in principle has those.
But are you saying that if suppose I had a renormalizable quantum field theory in AdS, it will give me correlation functions that don't have a then I do AdS here. I won't get a stress tensor on the boundary.
Mm-hmm.
But otherwise it will obey all the rules of CFT correlation functions, right?
Okay. Yeah.
So in that context, I would have thought that this could be completed without it.
Yeah. But I still don't understand this gamma 2 business. So the model that I have in mind is that the external operators are phi.
External operators by, and let's forget the stress tensor for a minute.
No, that's the single trace operator that's causing all this business. Phi don't interact with each other.
Wasn't he talking in a context where it was just like Polchinski? There was no
Yeah.
single trace.
Well, that's probably here, but in general, the thing that he
Yeah.
comes up with
In general, there could
was
be.
for some
There could be, but is there already a question where there is no other single trace operators? Could I look at a situation where I've got just quantum field theory in the bulk? Wilson-Fisher theory in the bulk, let's say, something like that.
Yeah.
QCD in the bulk. Okay. Some well-defined theory in the bulk. That gives me completely well-defined rules. It will give me generate some correlation functions on the boundary that have no stress tensor, but otherwise should be totally well-defined.
Yes.
Right? Now, what are the new operators in that language? Are they multi-field operators?
Multi-field. Yeah. There should
Higher
be
traces?
higher traces. Yeah.
Okay, because the higher loops are coming. That's
Yes.
what you're saying, right?
Yes. Yes.
Okay, good. So the new operators are just that you generate all the loops.
Yeah.
But you could do that systematically or not. Can you account? Would you be able to use Bootstrap? completely complete that solution?
In principle, I would think yes, but as you go higher orders, like there, the complication appears because of the sums and all. But in principle, I would think yes.
So you will be able to use, you think, Bootstrap to generate the full loop expansion of the bulk theory?
Yes. Except the fact that I can't really see how would you fix the OP coefficient of the new operators appearing in the higher loops.
But you're saying that those new operators were needed.
They would be needed, yes.
So then they will be needed with some coefficient.
Yeah, some consistency has to be there.
Either you could omit them, or they will be forced to appear with a particular coefficient.
But I would imagine that you have to do analysis. Yeah. I mean, they can be fixed by considering the 4-point function of other operators. Yes, they can be fixed.
So,
yes.
so you would say that you could just complete the whole theory this way.
Yes.
Okay, that sounds fantastic. Now let's suppose we try to do it with a theory with just stress tensors. Now let's get more ambitious. Let's say the boundary has only stress tensors, the bulk has only gravity. Could you use this to either define a pure quantum theory of gravity, or to prove of pure gravity, or to prove that none such exists? Right? It sounds like what you will do is generate a method to order by order systematically compute loops in the bulk.
Yeah.
That's quantum gravity. Now, either you should be able to take this to all, in principle, I don't mean that you can calculate it right, but in principle, either you should be able to take this to all orders,
Yes.
or what is more likely, show that this is not consistent.
Yes.
Yes, you think?
I mean, I think it's possible to do at least the way we are doing it.
So you think that you can either demonstrate that there exists a theory of pure quantum gravity,
Yeah.
or show that none such exists.
Yes.
General.
Yes.
That sounds like a totally very important result of genetic inference. Is it practically, I mean, what?
So okay. So
what
let
are
me.
the possible obstructions? How could you imagine that it might not work? What would fail? From the way you're saying it, it sounds like you will always be able to fix it up.
Yeah. I mean, if I know the if I know the interaction completely, then yes. I mean, I would imagine you can always do that.
So it sounds like
You may require some other operators.
you may, but where will that come about?
It's the ratio, I think we talked about that, the ratio of the double trace coupling to the single trace coupling, I mean the loop counting parameter, and then the string scale will appear correspondingly with respect to L. So you have some N, and so you can estimate the place where this operator will appear, will have to appear.
I'm sorry, what is that?
Well,
Which might be the Planck scale itself, you said.
well, not Planck's scale, the string scale.
But suppose I'm looking at the first corrections coming from loops. I'm trying to, I'm looking for a theory in which all those other operators are pushed as high as I possibly can. So corrections are not coming from exchanging single trace operators, but loops or gravitons, like M theory.
Yeah, but now I'm assuming that there is a loop coupling parameter, there is a small coupling expansion.
Small coupling expansion, there's loop coupling, like large M.
Not large N, I mean large G string also.
Small
Maybe
G string.
Small G string, yeah.
Small G string. I see. So that there is a classical theory.
Yeah, there is a classical theory and then there is a quantum theory with some ratio, and I'm seeing that ratio times N would estimate the place where the new operator should appear.
But suppose I want to ask something more ambitious. I'm looking for a theory in which there are genuinely no operators other than double traces of gravitons, multi traces of gravitons, and then at some very high scale they may get very connected. This would be a theory of pure quantum gravity, where the only field is the graviton until you reach black holes.
So it's like M theory.
Like M theory. Yeah, and I want to check whether such a theory exists.
So the assumption is that
It's like
except double field operator, there are no other.
double and triple and quadruple and so on, but that's the full spectrum. And then it can get corrected if you force, when the anomalous dimensions of these get very large.
Okay.
Isn't this a context you could work in? It sounds.
Yeah.
What you're doing.
I mean, but right now we have only gone up to order G square, but.
No, but I was just wondering about the structure. Can you imagine what would go wrong if, under this assumption, I kept trying to correct things up? Where will it fail? mean, it's a very vague question. I'm sorry,
Why will it fail?
but it sounds very interesting.
So just to understand the question again, I mean, are you asking like where those extra operators will appear? That is the question. Is it only the multi-field operators, or you are talking?
I want to think of a theory where only multi-field operators exist until you get to energies that are high enough, such that the anomalous dimensions are comparable to the dimensions of the operators.
Okay.
In which case, it makes no sense to talk about multi-field single.
Okay. And then your question is like where?
Firstly, I want to see whether such a theory exists. Secondly, I want to see, but it sounds a little bit like you're saying you can uniquely fix all the loops in such a theory.
Up to analytical terms, yes. I mean, the loops will have pole piece and analytical piece.
Analytic being contact terms.
Contact terms, yeah.
In the
Yeah.
maybe that's
Those you can't fix.
maybe that's those are like that's exactly the problem people have in renormalizing. Order by order, you add higher and higher order counter terms, which are the analytic basis. Maybe that's the maybe what you will do is exactly reproduce the renormalization program of quantum gravity. Now that sounds plausible. That sounds more plausible than uniquely determining what.
One should get to MKV.
One should get to it somehow. Yeah, but you may need it. Right. But since he has these contact term ambiguities, in M theory those contact term ambiguities are somehow fixed. It's some deeper principle.
You can apply that.
Yeah, whatever it is.
Regime bound? No?
But Reggie bound applies, in
Classical domain.
yeah. This is I'm a little worried that we're applying it in a place where you can't ignore the loops. Of course, as we discussed before, it's a stronger Reggie bound than the quantum. Maybe we can apply. Maybe that's the principle.
Yeah. So regarding this, to go to all loop order, we are working in a very simple system in 1D context. So in a 1D, since there are no large spin or anything, so you can assume that your CFT has only 2 delta phi plus 2n kind of operator. So only double field operators. There are no other operators. So in that system, we are trying to go to higher and higher orders and see what is happening. So right now we are again at order g square, but g cube is what we are looking at right now. But there the reason is to understand the structure of the correlator. Like there are certain transcendental function that appears at each order in loop. So we are trying to understand like what are those functions, like can we systematically understand them, and that context is simple enough to probe such questions.
Do you understand what is happening at quadratic order? How is one getting to quadratic order?
How is C2 being determined? C2 and gamma 2, that's the question.
Yes.
I don't understand many detail, but my picture is what he said, that
No. Yeah.
that suppose you have a four particle interaction, at some point these two things will come and there will be a loop.
No, but if I just do it from CFT, right, I don't have any a priori expectation
Yes.
about this vector.
Yes.
So you are saying the only operators I have are the double field operators.
Yes. Yes. So my rough
But
picture.
why can't multi-field operators appear at quadratic order?
It's probably because of because the multi-field operators already have a higher power of coupling constant to be created, and then there's the suppression because of the double discontinuity.
No, but why multi-field operators have higher power? I don't have any AdS picture, just consistency.
Let's say we're doing large n theory.
Okay.
Then 1 by n counting will tell you that 2 going to 3 will be suppressed by a higher power of 1 by n. So if you just solve everything systematically in a 1 over n expansion, at any given order in 1 over n, only a certain number of traces will appear. That will basically be consistent with Luke and the work.
So your status is that for this 5 to 4 type interaction you have square. I mean.
Yeah,
features are
order
square.
g square. Yeah.
So there you exchange all the double trace operators.
Yes. Like when I'm doing the calculation, it's just an assumption that at this order there is no other operator.
And then the cubic order you will take 5 cube.
At a?
At the next order you will take 5 cube.
At the next order, yes. I mean, if it depends, like if the theory has Z2 symmetry, then
Yeah.
those can, but yeah, like higher.
Yeah, that would precisely match the 1 over n complex. So in a 1 over n, if that was the context, that would be logical.
Now the primaries would be double tower.
Yeah, yeah, much more complicated. Yeah. Except without the del square equals 0.
Yeah.
So,
Which basically is the bulk statement that two-loop diagrams are much more complicated than one.
But this program, you think can be accessed just that? I don't like stress tensors as extreme.
As I know.
So if I have scalars,
Yes.
probe scalars,
Yes.
and I want to compute that 4-point position quantum gravity,
Yes.
can I not use this 1 over n counting and to produce to get the M theory?
For M theory, presumably you need the scalar to be one of the scalars that appears. You know, you can't mess around with it. But let's say we take one of the scalars that appears. Okay. It complicates things because you have to take the whole consistent truncation, the whole thing.
No, I mean, even the same thing is true for gravitons, right?
Well,
Gravitons, you are saying only for gravitons one can do this.
well, you know, we don't know of any theory which is possible. That's why it's interesting. Question: does a theory of pure gravity exist? Classically, it exists.
So when
Anything?
you mean in 3, you mean in some sense, right? Some approximate sense.
Some sense but the full supermultiplet. And then if you do it in AdS, you want the orbital section, right? So it's quite a big addition.
No, but I can ask this question about external scalars and quantum gravity.
Mami, can you call you back? Sorry.
No, I can ask this question about just external scalars and quantum gravity also.
Yes,
right?
you can ask that. Let's ask that. So go on. What is the
So
question?
now the question is, at the next order, I want to get this gamma to C2 by exchange of 2 gravitons.
And you're going to just minimal coupling of the scalars with that.
Yeah.
Scalars have no scalar-scalar interaction.
No scalars.
So all interactions happen through graviton exchange. Yeah. So it sounds sort of similar to, conceptually similar to having. Yeah. Okay. Fine. Yes. I agree. You could put it.
And then one should be able to complete this.
Yeah. So then now you have one graviton exchange is leading order, 2 graviton, so that's a 1 loop graph, 3 graviton is a 2 loop graph, and so on. But as he says, I think the issue will be that unless you apply some deeper principle, you will keep getting analytic ambiguities.
Yeah.
Right? And we can probably estimate what those analytic ambiguities are by the divergences of quantum gravity. Right? At n loops in quantum gravity, we get certain kind of countercurrents. They grow higher and higher. Yes. And then there will be some deeper principle at work to fix this.
But as an exercise, I mean, as a beginning thing, one can even look at full Fourier theory of scalars right in the bulk.
Yeah, forget about stress tensor appearing.
Yeah.
Yes.
Just the scalars and getting all of that.
Yeah, so but I think that even in that context, will you keep getting analytic ambiguities? You will. On the
Yeah.
other hand, you could work in a situation where the field theory in the bulk was totally well defined. So we could work in a the AdS3, Wilson-Fisher theory in the bulk. We don't want gravity, so we're not scared by AdS3. Okay, so we could work in that context. The field theory produces the answer with no ambiguities. But his procedure will not produce the answer with no ambiguities. So somehow the field theory is doing more. It would be nice to understand what the more is.
No, but his answer will not would be ambiguous only if you allow for these things at tree level, right? Tree level, if you allow for I mean these ambiguities are already arrived at tree level.
You're saying they just renormalize the tree level coupling.
Yeah.
But in the field theory says, okay, right. Now there are many things we could do. One thing we could do, I suppose. But suppose we demand that the bulk theory was conformal. So just understanding that, if we could understand why, what in the boundary sets, I don't know why it's natural to work with the conformal field theory. Maybe that's not natural. I don't know.
So
Kausik, I'm really sorry, but I'm going to have to go.
yeah, sure.
Please continue.
Just to answer your question again, like if you have a singlet, then what will you do? Uh, so, so this is how you will fix in the usual bootstrap. Okay, so it's more natural there, but okay, I never have used usual bootstrap to fix gamma 2 in that context, but like I know what they do. So what they will do is the following: in the next order, you have produced a term like log square u, right? Now, what is that correspond to in the T channel? That will correspond to log square v, right? Now, each block that you have here has a singularity like log v. So, so here, I mean, you have to do a resummation in the sense that you have to do a large spin summation, so that you produce from log fit, you can produce a log square v. So what you will do, you will assume that gamma 2 n comma l has some fall off, like 1 by l to the power something. This something will fix by looking at, like when you are taking these blocks, then you have to take the larger limit and do the sum, and you will see that you have to fix this to be l to the power delta phi, so that you get a log square v. And you also get log square v from these terms. This term, I mean, so you are comparing terms like log u, log square v. So in the left hand side, this term will contribute, this term will contribute, and this term will contribute. So these three terms you have to equate to log square v coefficient in the right hand side, which you again calculate back by doing the calculation here only, because T channel it's hard. So you take this, you compute the contribution of log square u, then you just exchange u and v to get the log square v. And then you compute the contribution in the S channel of this term, and this term. You do just the large spin resummation and you fix each term one by one. Or you can also use the method just I described. But you will end up getting an infinite sum, because this L, I mean for any L, this gamma is non-zero. So all the spins will contribute. In that sense, you will get an infinite sum. But that is the procedure, I mean the usual bootstrap. It's same as like usual thing. I mean in the first order, actually you get a divergence like v to the power delta phi minus tau by 2. To reproduce this, you resum for log v, but here you have log square v, so you have to do this. And that is the systematic also to go to higher order. You generate log u to the power n, so one power higher always, and to get that power you have to do a large spin summation, and you will fix term by term. And then the last part that I wanted to say about the loops, like how do you get the loops? So in a theory like which has a effective field theory description in the bulk, like Polchinski like. So in those theories, the non-zero spins, the data, like the corrections it is getting from non-zero spin is only this, right? Only this space, because non-zero. So this is non-zero only for L greater than some L naught. And this is non-zero only up to L equal to L naught. So for such spins where L greater than L naught, we'll get the entire contribution from loops, right? Because this will be correspond to some tree like thing, but this will entirely come from the loop, right? So the following picture I have in mind, like you are basically have a 4-point function, and then you have a measure, and this is the Mellin amplitude. So there is u to the power s, v to the power t, and then you have a expansion like m tree plus m loop by n square, And the similar thing here, so G1 by n, only the connected piece, so G2 by n square. And this is G2. This whole summation is G2, and that will relate to M loop. So what I was trying to say, that M loop will be related to, like, the L greater than L naught term will come from this. So what you have to, now what are the things that you can say from here? One thing that you can say from here, you know that there is a double pole in at s equal to delta phi plus n. But here you are getting a log square u term. So here the only kind of thing you will get is u to the power delta phi log u, that comes from measure. So loop must have a pole at s equal to delta phi plus n places, so that it's a triple pole, and from loop you can get a term like log square u. So that's how you are predicting a behavior for M loop. So you can write like M loop equal to plus the crossing term, I mean s goes to t plus del phi and delta phi minus s by t. So that's crossing symmetry. And there is plus regular term, and we can't say anything about the regular term, but this RNs can be fixed. And how that can be fixed? By picking up the power u to the power delta, like now plug this unsuch here, and then you pick out the pole for s equal to delta phi pole, and that will be like u to the power delta phi log u. So that u to the power delta phi log u, you compare with the non-zero spin part. And then again you can take only n equal to 0. And if you take, like, that is sufficient to fix the RNs. So if you just take n equal to 0, then again your block will be just that 3f2. So basically you use the orthogonality, and then if you take the large spin, you can fix all the RNs. Like, that's just exercise that you can do. But so in this way, actually, you can compute diagrams. For example, something like this bubble diagram, or this diagram. And you can do more, but these two like easily can be done. And this was known before, but this was not known before. So this way you can fix at least this diagram up to the regular terms that you can fix. So yeah, that is what in the loops.